Okie dokie. Can everyone hear me?
Yes.
Thank you. Where's the chat? There it is. Okay. So, Duke is like walking around the house. So you might hear him a lot walking. I'm sorry about that. This is just a reminder that homework 6 is going to be due on Thursday, as always. I'm working on test corrections, but I have a few assignments due tomorrow, so those will be done graded by Thursday. Yeah. And then we're going to do a quick review from homework 5 today because there's a few quick comments that I needed to kind of make for everybody. So I thought I'd also make them on top of your comments that you can see on Blackboard. I also wanted to comment on them in class. And then we're going to finish up 2.2 and hopefully finish 2.3. A lot of definitions in 2.3, but hopefully shouldn't be anything too new. And that was Duke this morning at the dog park with his little ball. That's his little glow-in-the-dark ball. He's just like very happy. He looks very fat. But I promise that he is only mildly fat. Okay, does anyone have any questions about what we're going to be doing today? Okay. Is the chat working? Oh, okay. Thank you. Great. So let's go over to homework 5. I think I posted these solutions. I don't think I actually have yet. I wanted to go over, right, so this is homework 5, right? You had problems at 1.5 and 1.7. Function notation. In this problem, you guys were asked to, if it was a function with x as the independent and y as the dependent, meaning like x is a function of y in part A and flipped y is a function of x. Wait. Yes. And then if it's true, express the equation with function notation. Function notation is instead of having whatever my output is, I have something like this, f of x, or it's like f of my input. So since x is the independent variable, I would have f of x. And in the second case, where y is my independent variable, I would have f of y. So that was the point of asking you if it's a function with this variable as the independent variable. All right. You didn't have to use f, you could use g or whatever letter. But this is the function notation. Is that clear to everyone? The difference of saying like y equals or x equals and saying like f of x and f of y. Or does anyone else have any more questions? Okay, cool. This one you guys did pretty great. On my solutions, I didn't say what do these values represent. So I need to that's why I didn't upload them because I hadn't done that yet. Okay. Real quick. For the ones in 1.7, there are two big things. You guys were asked to find the local maximum and minimum values. Majority of you all were able to give me the local max, which is at this little point right here, but there's also a local minimum. Does anyone see where the local minimum is? On the graph? Oh my God, I just got 3 different answers. So local minimum, we're wondering, looking at this graph, that is this graph of x square root of 6 minus x, where the local minimum occurs, or what is, sorry, where is the local minimum, right? So the local minimum is a y value, right? So Abby said y equals 0. And by y value, usually we mean just like the output, even though we are given f of x. Y value is nearly synonymous. I actually don't know what synonymous means. And then you say when x equals 6 when you're asked for the value of x at which it occurs. So endpoints, when I say endpoints, right, like I will talk about more directly endpoints, but remember when we did the problem in 1.7 when it was like a semicircle and the minimums were at like -2 and 2. Those were the endpoints of the domain. So even though this point right here only has things to this side of it, the left side, I don't know my lefts or rights very fluently. And it has nothing to the right of it because I can't have any x value bigger than 6 or I'm going to be taking the square root of a negative number. It's still a local minimum, right? It still fits it that everything in the close neighborhood around it is still bigger than it. So it's still a local minimum. It's not a global minimum. I still have numbers that are way smaller than it, like, oops, sorry, like all of these down here, but it's still a local minimum. And Griffin brought up negative infinity, and I saw that solution a lot. Negative infinity as a minimum and infinity as a maximum is, right, like a local minimum is at a specific point. Can I ever obtain negative infinity? Can I ever just hold that in my hand? No, right? So it has to be some attainable number. If you're going to say that a local min is at negative infinity, then there is no local min. It's kind of like what's bigger than, or what's smaller or more negative than negative infinity? Well, negative infinity. It's not like a set number. So that's why you can't, it's not really going to be a solution. Does that make sense to everyone? I don't know why we're like walking around. Okay. And then another thing I saw from a lot of people were that you're writing your increasing and decreasing intervals as, yeah, we can never have negative infinity as a local min or infinity as a local max, like two ends of the spectrum. I can't have infinity as an option. That I would like for you to tell me where the local min is at, and I ask for like an XY coordinate, then I would basically like have to write a point that's like to infinity. Like it doesn't make sense. Also, where does that minimum occur where it's actually negative infinity? Like you can't write that. It like doesn't. It's like the tallest point of the earth is like infinity because I can just keep going up and up and up. But where do I attain that infinity on earth? Nowhere. Spacey. Okay, cool. Anyways, increasing and decreasing intervals are open intervals. They're not XY points. Sometimes people will say from this XY point to this XY point. That's not how we write intervals. If you're confused about how we write intervals, I would review chapter A. We talked about intervals. They're always open. Some of you were telling me that I'm increasing up to and including 4, and I was also decreasing up to and including 4. How can I be increasing and decreasing at 4 at the same time? I can't. So that's why they're always going to be open intervals, which is kind of nice. I don't have to think about if I'm going to include these points. Even at this endpoint, 6, I'm still not going to include it. It's always, always, always an open interval. Okay. And then for 1.7, problem 50, I'll give you guys a coughing problem. Hope you learned a lot about coughing. There's a really important part of this problem that when you guys were writing down your problems, if you wrote your problem, you guys included, but then it didn't ever follow through into your whatchamacallit, answers. So we talked about this when we talked about domain, and I try to be very purposeful about it. I'm given this function, right? V is a function of r. I can write v, the velocity, as something with, what is r? The radius of the trachea. And so on. So, but I'm also told that r is between 1/2 and 1, and that needs to follow through in my answers. Right, this is like a real life problem. I would be very concerned if someone's trachea had negative values. I don't know what that means for their vocal cord, but I'd be very concerned, especially if a trachea was like 24 centimeters. That's ridiculous. Who are you? You're giant. Right? So we need to pay attention. This is telling me that R is restricted to this domain. I like to call it like a specified domain, like one that's not induced by the problem, where if I would have it like divided by 0 or square root of a negative, those things are induced in the function. But this one is just, I'm told R has to be between these things, like the real world specification, right? And that like drastically changes it, right? So when I graph my function, it's going to look something like this, just this little bit of it. A lot of you were giving me there's Winston, like whole entire graph. What is the equation again? 3.2, 1 minus r. Okay. 3.2, 1 minus, we'll say x squared. And a lot of you were showing me something like this. Okay, I'm like zoomed out a lot. If you grab onto the axes on Desmos, you can like fix the thing, right? So some of you were just giving me like this whole thing. But what I really want is just that little smidgen that I had before, right? Because that's all I care about. Right? So then you're asked increasing and decreasing, and some of you guys were giving me things into the negative infinity. This is a real world problem. I can't usually have negatives involved in the first place. So we just want to look at this little section of the graph. Does that make sense? And how parts B and C are going to come from this graph, and it's going to change a lot of the local mins, right? Because I have those 2 endpoints, which I don't think you actually need to find a local min. I think you just need to find the max. Yeah, so you didn't even find any min, but it definitely affected your increasing and decreasing. Is this making sense? A little more engagement from others would also be very helpful, because only one person got this correct on their homework. So I want to make sure that it is actually making sense to everybody. Okay. Because you will be seeing a problem like this again. Alrighty. So those are my comments on that homework. Did anyone else have any questions about this homework at all? Oh, I know, it's okay. Written part is only half of your homework, and 2 of your lowest homework grades get dropped anyways. So careless mistakes are forgiven. It is okay. Alrighty. So sorry if you hated that noise. Okay. So last time we talked about average rates of change and everything, and then we talked about linear functions and how they always have a constant rates of change. And we like to see them of this form usually. F of x equals mx plus b. And then we talked about which graphs were linear and not linear. And then we found the average rates of change between all of them. And we found out each time, even if I wasn't even given numbers, right? We did it with x equals c and x equals d. I'm still getting the same number out. If it's, even if I'm varying the size of the interval, right? So we deduce from there that m in our f of x equals mx plus b is our slope, and it's also the average rate of change, which is constant. And then I asked you guys really quickly if 3 minus 4x divided by x is a linear function. Who can tell me if this is a linear function or not? I have 3 minus 4x divided by x. Is that a linear function? No, it's not. I have x in the denominator. Linear functions, x is just to the first power, not -1 like it is down here. It's to the first power only, right? So y equals mx plus b. I can't rewrite this as, I would get like 3 over x minus 4x over x, 3 over x minus 4. Yeah, no, that is not a linear function. This is actually, I was gonna say a logarithmic function, but I don't even think it's that. It's a crazy function. So that is not a linear function. If you got this problem wrong, I would highly recommend paying closer attention today. All right, cool. So we're going to talk about more attributes about linear function and rates of change, right? So in section 2, called linear functions and rates of change, we saw that the average rate of change of f is the constant m, right? They're constants because they're going to be numbers like 2 and 3 or 3.5, 4 over 7, something like that, a constant. X is a variable that I can just change and plug in something and I'll get something back out. But m and b are constants. And in this case, b is going to be our initial value. Okay. So with that, we can use that knowledge right there to come up with some linear functions. So if water is being pumped into a swimming pool at the rate of 5 gallons per minute, so water's being pumped. Okay, initially the pool has 200 gallons of water. Find the linear function that models the volume of water into the pool at any time. Okay, right, so I like to draw pictures for these. Right, I have this pool. We'll draw an above ground pool, one of those like big brown blue ones. Has like the fun little ladder. Anyways, so I only have like 200 gallons of water in it, right? So let's just say that like it rained overnight or something and just have some water in it, rainwater. But I want to keep filling up. So I'm going to grab my green hose and I'm going to fill it up. I know I am an artiste and you all are very jealous of my artistic abilities. Right? So that's what's happening. The water level is rising. So I want to find a linear function that models the volume of the water of the pool. So we're modeling water, so I'm just going to call our function v of x. I usually like x to be our variable. All right. So it's going to be, oopsies, mx plus b because we're told that it's a linear function, right? So what's m going to be and what's b going to be and why? So y, what is m? CJ, why is m going to be 5? Right, it's our rate. we're told that it's going in at 5 gallons per minute, and it's a rate of, rate is a really key word, right? So our rate is going to just be 5, and then our B is going to be, I think a lot of people said it, let's go down, is 200, right? That's my initial value initially. So it's kind of using these, like, I'm about to call them spicy words, like keyword hit points that kind of fall into what these words look like, right? So with that, I can then just say that it's going to be 5x plus 200. And that's it. Is everyone okay with finding linear functions like that? Can I get a thumbs up, thumbs sideways, and thumbs down? Okay, beautiful. Love all the responses. All right, cool. So now we're looking at linear functions and slopes. Remember, slope came from M. And we're gonna kind of be doing them a lot from graphs. So when looking at a graph, we care about the graph's steepness. We kind of talked about this last class. Or how fast it rises and falls. The steeper it is, the larger the number, or more negative the number. The flatter it is, the closer to 0 the number is. All right, so let me scroll through my outline. There we go. And we've kind of talked about this already, that the slope is rise over run. And specifically for a linear function, M equals our average rate of change, which is also rise over run, which is also the slope. So now we have a lot of different things happening. We have M, we have slope, we have average rate of change, rise over run. They're all the same. It's like your one friend that always has like 5 different nicknames, or something like that. It's the same thing. Okay. So now let's do an example, because I think we're all pretty familiar with rise over run. I forgot to draw this graph, but below in a second will be a staircase on the coordinate plane. Right, so let me draw this really quickly. I meant to do this before class, and I did not. So 1, 2, 3. And then this is. All right, we're gonna do this in this like fun brown. And those are your stairs, right? Okay. So I'm then gonna draw this red line on the trim. The trim is like the edges. And act like those all line up. Okay. So something like that. There we go. Okay, cool. So the red line is the edge of the trim board. So find equation for the line. Right? Obviously the brown lines, those are the stairs. Those can't be functions. Why can't those be functions? Why can't this stair be a function? It's not linear. Well, we have more than just linear functions. It doesn't pass the vertical line test. It's a vertical or horizontal? Yeah, it doesn't pass the vertical line test, right? I have these like straight up and down bits. So that's why we're not modeling the stairs here, because it's not even a function. Great job, guys. So we're asked to find the equation of the line, the red line. All right, so right, f of x equals mx plus b. So I need m and I need b. Which one is kind of really easy to see just by looking at the graph? B, right? Abby, what's B going to be? Right, looking at the graph, b equals 8, right? It's our initial value. Initial is when my independent variable is 0. We also know this as the y-intercept, right? So then there we go. So I have that point there. So when x is 0, my tread is at 8. All right, so how do I find m? Or what's a way that I could find m? Because that's the only one I'm missing left. Rise over run. How do I figure out rise over run? Or the slope. How do I find the slope of this red line? Great, Ronald. Yeah. So how many units does it go up and how many units does it go over to the next point of the staircase touching the red line? We actually don't even need to do the very next point. So Ronald's talking about if I go, so my rise and then my running over. So I'm going from 8 to 16 and running over from 0 to 12. So this is like 8. And what is that? 0 to 12, 12. I don't even have to do that one though. If I really liked whatever this point was, which is probably, if this is going 8, 16, 24, I could do this point. I don't have to do necessarily the next one. I just need to find the slope between 2 points, any 2 points. I usually like to do the y-intercept because that one has 0 and subtracting 0 from something is super easy. And instead of like really hard things to subtract from each other in your head. But just the slope between any 2 points. Slope between 2 points on the line, I should specify. If you take the slope between any 2 random points, it's not going to mean anything. It has to be on the line. Right? So the second one that we're doing is 12, 16. Right? So my rise is also my change in y, right? And my run is my change in x. So I went from 8 to 16. So 16 minus 8 would give me 8. And then I went from 0 to 12. So 12 minus 0. And I get 8 over 12, which I should simplify to 2/3. I always think that one's 3/4. All right. Is everyone clear on how I got 2/3 for m? Thank you, Galicia. Okay, beautiful. Oh my gosh, people that I have not been hearing from are talking. I love it. Yeah, we're gonna have lots of different examples. We're gonna talk about I think let's see what the next ones are. We're not gonna do specifically one where we create the line next, but basically I would start by finding B, my intercept, if it's there. If it's not, I really just need to find the slope between 2 points to find M. And then, actually, no, I do need to find B. It's not going to be given. Yeah, I would find the initial condition and then find the slope between 2 points. Bada bing, bada boom. You're done. Oh, we're not done because we didn't write our function. F of x equals 2/3 x plus 8. There we go. Okay. Let's do some more of these examples and then see if we need to circle back again. All right. So now we have taken a graph and found the function. So similarly, we can take the function and easily find the graph. All right. So we're asked to graph f of x equals 2x plus 1. And by graph the function, I don't mean plug it into your calculator. I mean draw the graph. Right? So I'm going to just draw my axes. That's not straight. Okay. X and Y. So let's do 1, 2, 3, 4. 1, 2, 3, 4. Great. And if we wanted to, I could draw some negatives. Great. So looking at 2 plus x, what's my initial condition of that function? 2, right? So my initial condition is when x equals 0. So I go 1, 2, put that right up here. And then it's plus x. So what's m in this situation? I found that b equaled, not 8, what am I doing? 2. But what's m? It's 1, right? Good job. So that means for every unit that I rise, I run over 1 and vice versa. So for my next point, I'm going to go up 1 and then go over 1. Perfect. Next one, I'm going to rise 1, run over 1, and so on. And then I can even go down 1 and back another 1 and get that point. So now I have all these points, and then it's just a fun game of connect the dots. Hopefully this will make a straight line. So close. And that's how we can take a function and easily draw a graph without using a calculator. A lot of calculus is using properties of calculus to then, I can just give you a certain type of function and you'll be able to draw a graph. Just kind of how I took things that I knew from this function to draw it right here without a calculator. The 1 came from the coefficient of x, right? So the number outside of x, since there is no number, it's a hidden 1. 1 likes to hide a lot because it's just kind of invisible. Anything times 1 is just 1. Yep. Cool. So is everyone good from going from function to graph and graph to function? We like thumbs up, thumb sideways, or thumbs down on the function to graph transition. Great. Okay, cool. So now I need to draw a graph for this one because I forgot to do that too. So Mary and John, is John, Mary, Joseph like a songwriting band that wrote like a really cool song when we were all in like elementary school? I was in elementary school. Anyways, so John and Mary drive westward along I-76 at a constant speed. They got their cruise control on, or they have a Tesla. Below is a graph of their distance from Philadelphia at time X in hours, where X is 0 at noon. So this is very important. Let me draw this really quickly. Come on. not a straight line. Okay. So then 1, 2, 3, 4. Okay. Alrighty. One second, I just need to draw this really quickly. Okay, here's my beautiful graph. And I had to look at the textbook while I was doing it. Okay. So this is X in hours, and this is Y in miles. All right, cool. So that's our graph, right? So they're at a constant speed. So we're asked how fast are they traveling and who is faster and how does this show on the graph? So we're asked like a lot of things. So how can I find how fast they're going? Looking at this graph, how can I figure out where, right, rise over run, right? I need to find the slope of each of their lines because I'm already told that they're at a constant speed. So we're given 2 points for Mary and John. So for Mary, we're given 0, 0, and this other one is at 2, 150. So that's Mary. And for John, he started about 150 miles away from Philly already. And then after 2 hours, he's somewhere around 250 miles away. Also, there we go. So blue is for John. Alrighty. So I'm gonna take these with me. Right. Just so I have these points in mind. All right. So those are just 2 points that I got off the graph. Those were specifically highlighted in your textbook if you look at this problem. So how can I find the slope for Mary? So let's call it M sub M. So Mary's slope. So like if you were describing me how to calculate her speed, what would you tell me to do? What if I don't know what rise over run means? Right, I would do the change in my y's, so y2 minus y1 over x2 minus x1, which would give me 150 divided by 2, which is equal to 75. We can't really stop there because we're asking how fast they are, and this is in miles and hours. So it's going to be 7 miles per hour, which we have a fun little thing for, right? So I'm not just finding the difference between them, I'm dividing the difference too. We need to be really specific about our words. So let's find the slope for John. So MJ, we're going to do 250 minus 150 because he already started farther away, and 2 minus 0. So 100 minus 2, which is just going to be 50 miles per hour. John likes to drive like a little man, drive slow. Right, so who's faster? Right, Mary is, right? Because she has the greater, more positive slope. So Mary is driving faster. And how does this show up on the graph? If we look at this graph again, knowing that Mary is driving faster than John, right? It's a steeper incline. So we say which shows on the graph as Mary's steeper slope, or incline, if you will. All right. So now we're asked to find functions for their distances from Philly. All right, so let's call Mary's function like m of x, and we'll call John's j of x. We've already done half the battle, right? We've already found our slopes, right? M and j, that's how fast they were traveling. So, right, it's going to be mx plus b of m. And here I'm just using these subscripts so that we know we're talking about Mary's slope and initial value, and John's, just because sometimes color isn't as clear of a differentiator. Is anyone colorblind? Do these, oh my gosh, are these colors different? Which colorblind are you, Griffin? Oh, okay. I think red green is the more common one. Blue yellow is like not as common. Oh. What colors am I talking about? CJ, what numbers are you asking about? About the 750 and the 50? Or 75 and the 50? Or, oh, those are from the graph, right? So I go up here. So this is like between 200 and 100. So I'm just gonna say it's 150. It's kind of more clear on the graph of the textbook. They have like little things. And similar for this one, it's like halfway in between 200 and 300. So I just assumed 250. Is that clear? Yeah, perfect. Okay. Great. So, all right. So what is going to be the initial value for Mary? And what is going to be our initial value for John? Right? Looking at this graph, what is Mary's initial condition and what is John's? So Mary's is 0, right? She's like smack dab right at the intercept. And John's is, we're going to say about 150, right? We actually kind of already had these points right here, which was really nice. So yeah, b sub m is going to be 0 and b sub j is going to be 150. So in tandem with part A, since we already found m and j, our slopes for each one of them, what is Mary's slope? 75. So 75 x, and we're not going to put plus 0, a little redundant, but. And then for John, we're going to say, what's his slope? 50x. plus 150. All right. How do you guys feel about that so far? Great. Okay. Remember, we're grabbing our slopes from the part A. We already found, right? Average speed is also the same as average rate of change, just a special case when we're talking about distance and time. And that's already going to be what we found earlier, our slopes. So we just need to find our intercepts. All right. So now we're asked to how far they have traveled at 5 p.m. So let's go up here and just double check that x equals 0 at noon. So this is going to be like noon, 1 p.m., 2 p.m., 3 p.m., and so on. So what's x going to equal at 5 p.m.? 5, right? So I'm going to find Mary's distance after 5 hours. That's like the really great thing about this is function notation. Remember, instead of saying like y sub m, right, for the output of Mary. It's really nice to use function notation because I can say this is Mary's distance after 5 hours, all in one thing. Right, and then I'm going to plug that into, oops, sorry, wrong color. M of 5, there we go. All right, so 75. I'm just going to plug in 5. I'm going to pull out my calculator for that. Because, actually, no. 750 times 2 is 150 times 4 is 300 plus another 75 is going to be 150, 300, 375? 75 times 5. Yeah, 375. And then where's John at? His is 50 times 5 plus, remember he got like that's gain on her of another 150 miles. So what is that? 5 times 50 is 250 plus another 150, 350, 400. 400 miles. All right. Thank you, Gilicia. So do you see that Mary's kind of catching up on him? Right? They started at noon. Mary was at 0 and John was 150 miles away. But after 5 hours, she's only 25 miles away from her. So would Mary eventually catch up to John and pass him? What do you guys think? Yeah, right? So eventually, going on and on and on, their paths are going to cross. And we'll talk more about that in the following sections because we are done with this one. Yay. Okay. How do you guys feel about linear functions so far? Give me a thumbs up, thumbs sideways, or thumbs down. Great. Okay. So now we're going to start on 2.3, wherever it is. My notes, there it is. Nope, that's 2.4. 2.3. What's today? It's a Tuesday. It is March 9th, 2021. Oh my God, if it was like a normal time of year, this would be spring break. Sad. Okay. We've already talked about making linear models from like real problems and stuff, but we've kind of only seen the traditional way that we've always talked about y equals mx plus b. So we talked about initial value, what that's our b, and average rate of change, which is m, which we also call slope. So now we can kind of get into some nicer definitions. we've like graduated into like nicer words, right? So instead of initial condition, we like to call it the y-intercept, right? It intercepts or intersects the y-axis, right? It's the y value, just like local max, local min, or it's just the y value, not the point, for when x equals 0, right? So when I say it's a point on the x-axis, I mean it's like that guy right there. That would be where my y-intercept is, okay? I think we're all pretty familiar with that. We have 3 different ways to write the equation. We're going to talk about 2 of them right now, and then later on we'll talk about another one. So the names are pretty self-explanatory. The first 2 are, because it kind of tells you what's in each of them and what you need for each to write each of the equations. Equations, yeah. Right. So the first one, I think we're all pretty familiar with, is called slope-intercept form. Does anyone know what this one looks like? Anybody know what slope-intercept form is? Yeah, y equals mx plus b. Right, where m is our slope and b is the y-intercept. So all I need to make for this one is my slope and my intercept. And that'll give me the slope-intercept form. You will, and you are expected to know the difference between them. And if I give you a function or give you an equation of a line and I ask you to write it in a specific way, I will take out points if you don't write it in that specific form. Just as a way that if I asked you to factor by completing the square and you did it by quadratic, no, doesn't work like that. Okay, so you need to know all these forms and know what they look like and be able to write them. Okay, so the second one is called point slope form. All you need is the slope of the equation and a point, right? And that one looks like y minus y1 equals m times the quantity x minus x1, where m is the slope, naturally, and the line passes through the point x1 and y1. So x1 and y1, when I write this out, are just numbers, okay? And this actually just comes from the definition for slope, right? Remember, it's going to be like, what is it, y2 minus y1 over x2 minus x1. And I'm just multiplying each side by x2 minus x1. Do you see how that I got there? It just comes from that. That's pretty cool, right? In this case, x1 and x2 are just x and y. Do you guys see where point slope form came from? It's pretty great. General point slope is the easiest one to acquire if I'm just given points on a graph, because sometimes I'm not given where the y-intercept is. You need to see if my graph is scaled to the side or something. If I'm just given a graph and I have 2 points, find the slope between those 2 points and then smush one of those points back into the function, point slope form. Boom. All right. So in these examples, we're not asked to produce any form. So we're kind of free to do what we want. So we're asked to find the equation of the line with a slope 3 and intercept -2. So slope 3, here, I like to highlight in my problems. So slope 3 and intercept -2. Right, so what's that equation going to look like? It doesn't matter what form we're putting it in. Yeah, 3 minus 2x, right? We could write it in point slope form, but that would take a lot more time. Right, and the -2 comes from the intercept being -2. All right. Problem 2 just says to write 3y minus 2x equal to 1 in slope intercept form. So remember, sloped intercept form is y equals mx plus b. So the most important thing here is I just need to get it first to y equals. So I need to solve for y, basically. So 3y minus 2x equal to 1. what's a step? What's something I can do first? What's a good first step to getting 3y minus 2x equal to 1 into slope intercept form, right? Adding 2x to both sides. So I get 3y equal to 2x plus 1. What next? And then divide by 3. Should I write y equals 2x plus 1 all over 3? Yeah, correct. I don't really want to write that. I want to separate them. I want something times x plus b, not something times x plus b all over another number. The point of slope intercept form is to easily see the slope and easily see the y-intercept. Writing it like this is not slope intercept form. Okay. This is. Alrighty. Woohoo. How are you guys feeling about this one so far? Feeling good? Feeling groovy? The first one's not right because I don't have y equals mx plus b. I have y equal to a number times x plus a number divided by another number, right? It's like y equals ax plus c over d. They're not the same. Number times x plus another number, not divided by some other number. The point of slope intercept form is that I can easily reach into the function and grab it out. I can't easily reach in and grab the y-intercept or the slope. That divided by 3 is confusing me. Alrighty. So now I'm asked to find the equation of the line through 1, 3 with slope -1/2. So which form is probably going to be the best one to use for this one? Right? Point slope. I'm given a point, given a slope. Point slope. All right, cool. So point slope form, remember, is y minus y1 mx minus x1, right? I don't want to distribute that x, the m. I just want to keep m outside. Okay, so our slope 1/2, and that's our point. So remember, points go x, y, so x1 equals 1, y1 equals 3, and our slope is m, and it's 1/2, -1/2, excuse me. So that's going to make our function y minus 3 equal to -1/2 x minus, what's x1? 1. Okay? I'm not going to distribute. I'm actually not asked to give a specific form, but if I'm doing point slope form, I don't want to distribute that -1/2. Okay? So in all of these cases, I was given the slope of -1/2. I was asked to move this one, and I was given the slope here. What if I'm not given the slope? I just want to find the line that passes through, let's say, -1 and 2, and the point 3, -4. Rise or run? Give me some numbers with that, Ronald. Right, we know m is rise over run, change of y over change of x. How can I put that into numbers? Right, so I'm going to do -4 minus 2, and 3 minus a -1, which is going to be 3 plus 1 eventually, right? So -4 minus 2, that's going to be -6. And that's going to be +4. So that's going to boil down to -3 halves, right? Yeah. Cool. Great. So that's M. So we have a slope. Both of our forms for writing a line both involve slope. So which form should we use? I have a slope. So you intercept, or sorry, slope intercept or point slope? Point slope, right? I'm given 2 points. Does it matter which one I use? No, it doesn't matter. Right? So I can do y minus, let's say, 2 equal to -3 halves. X plus 1, right? Minus a negative. And that's, or I can say y plus 4, right? Minus a negative equals -3 halves x minus 3. They're the same line. They have the same slope. And I promise you, if I work these out and get to point intercept form, I'll get like y equals -3 halves x plus 1/2. I think so. If you work it out both ways. So they're the same line. I'm just writing them with different points. I could write it infinite different ways because there's infinite points on a line. Okay. How do you guys feel about finding the equation of a line by just given 2 points? Feeling thumbs up, thumbs down, thumbs sideways? All right, cool. So now we are able to model things that are like linear, right? Now it might not be clear. Here's a point, there's a point. We might be told it in a sentence form of where these different points are, right? So a vending machine operator services the soda pop machines. It's really cute, soda pop. In a freeway rest area, right? So he finds that the number of cans in the soda that he sells each week depends linearly on the price he charges. It's like supply and demand if you're in a business class. Where am I? Da-da-da. Prices that he charges. At price of $1 per can of soda, he sells 600 cans. So, but for every 25-cent increase, he sells 75 fewer cans each week. So we're asked to model above by a linear equation. So kind of, what am I trying to say? Like, a good place to start when finding models is identifying your independent and dependent variables. Also naming them just for your own convenience. So what is going to be my independent variable in this case? And what's my dependent? I only have 2 things going on. Number of cans, price is independent is price. Right, yeah, I would say my price. I can change my price and the amount of cans that I sell changes. So that's definitely dependent on my price. So we'll say price, and we're going to call that X, just because I really like when X is our independent variable. And our dependent variable, is the number of cans sold. Right, so let's call that S, specifically S of X. All right. Then let's not do S, let's do C, because it's cans. Right, so I'm going to model the amount of cans that I sold depending on the price. This is really important and it'll change the whole problem. Are we going to do, is the cost going to be in dollars or cents? Okay, Ronald says cents. Does anyone else have an input? It doesn't matter, but it does change the problem. Okay, we're going to do it in cents. Cents, right? So when I say $1, right, that's 100 cents. Remember, the little C goes after it when you're doing cents. Right, so that makes, at $1, I'm going to sell 600 cans. So that gives me the point, let's say $1 sells 600 cans. That gives me the point of my graph 100 and then 600. Okay. But for every 25-cent increase in the price, he sells 75 fewer cans each week. That can either, this can give me one of two things. This can give me rise over run, or it can just give me a different point. I would want a different point. That would kind of help me instead of trying to figure rise out or run out of that. Okay, so for every 25-cent increase, so every 25-cent increase, 75 cans fewer. All right. So that's going to give me, if I'm going to increase it 25 cents, that's so 125. How many cans am I going to sell? If I sold 600 and now I'm increasing it 25 cents, so he's going to sell 75 fewer. Yeah, 525. All right. And that's going to help me find my slope, just like we just did when I was just given the points. I had to work a little bit to get these points. But these are the phrases in the problem that help me get to each of those points. So remember M, I'm going to do 525 minus 600 over 125 minus 100. Right, so that's going to give me minus 75 over 25. This is the rise or run part that's kind of explicitly said in our problem, right? For every 25-cent increase of my independent variable, so that's my run, I have, right, that's my run, I have 75 fewer cans, so that's my rise. In this case, my rise is a negative. That's fine. And this is going to give me what, -3. I don't need units on my slope. Okay. All right, awesome. I actually don't need, it's not a, we're asking for an equation, not a function. So I don't even need C of X, I just need C. So what can I do next to find my linear model? Right, I have these two forms, slope intercept and point slope. I have my slope, So can do either one. Which one should we choose? Let's use point slope, right? So that's going to be C minus, what, 600? Equal to negative 3x minus 100. And that's our linear equation. I got rid of my function notation from earlier because it's asking for an equation, not a function. Okay. Is everyone okay with how I got this equation? Does anyone have any questions before we move on? Okay, coolio. So how many cans of soda will he sell if he charges 60 cents per can? And if he sells us $2 per can? All right. So at 60 cents per can, that's going to give me how many cans of soda? Remember, we made our price X and our number of cans sold C. So how many cans means we're looking for C. So we have C minus 600 equal to minus 3. And in this case, X is 60, right? So I'm just going to 60 minus 100. C, oopsies. C minus 600. 60 minus 100 is going to be negative 40. Which is going to be 120. I'm going to add 600 onto both sides. So that's going to give me, oopsies, 720 cans. Alrighty. Were you guys able to follow that, or did I go through that a little too fast? Hello? Okay. So now we're asked if it's at $2. Remember we said we're doing this in cents, so X would equal 200. So now we have C, oopsies, C minus 600 is going to equal minus 3, 200 minus 100, which is going to give me what, negative 3 times 100. So is that meant to be a C? So C equals what, negative 300 plus 600, which is another 300 cans. All right, cool. Anyone have any questions about that so far? How are we feeling? Thumbs up, thumbs sideways, or thumbs down about using a linear equation in word problems? Nice, nice. Okay. So we're going to do our exit slip. Oh my God, Duke is snoring so loud. Oh, let me open our exit slip. There we go. And our teacher question is actually going to be this. Part C, I want you to find the slope and tell me what does it represent. I really want you to tell me what the slope represents in terms of the problem. Don't just tell me rise or run. So I want to hear cans, increase, cents, decrease, something like that. All right. Yes, absolutely, Griffin. And I do post the skeleton note outlines to these. So all of chapter 2 is already. So if you if I ever go through like a paragraph problem too fast, you want to write it all down, it's on Blackboard. Because we will be getting to problems that are kind of lengthy. Let me see if I can like zoom out. There we go. Let me know if you can't read that and need me to zoom in. Oh, let me stop recording.